within 10 years of each other.
Mm-hmm.
And then the atomic model turns and looks like that.
Uh-huh.
And I have the kids draw each one of these circles in there,
Uh-huh.
and associate it with the right guy.
Uh-huh.
And then Ernest Rutherford comes along, and he discovers the nucleus. And we
Uh-huh.
have the next slide is
Uh-huh.
all about his experiment. We go into
Uh-huh.
that in huge detail. And that changed the atomic model look like that.
Uh-huh.
And then James Chadwick and I would talk about Jimmy Neutron, and why is Jimmy Neutron called Jimmy? It's because they named him after this guy who discovered the neutrons. And then we get into, now Chadwick is not on the text, but I get into how did he discover the neutron? Why did it take less than 10 years to go from protons to electrons, but then over 30 years to get to the neutrons? And I'm like, what's the deal? And so that's when they have to realize, oh, neutrons are neutral, therefore the experiments that they were doing for the protons and electrons wouldn't work because they're not going to be attracted to positive and negative charges. And the kids, you will get some kids that will figure that out. You don't have to tell them. They should be able to say that. And they're like, okay, well, what does a neutron have that would mean discovered? And they usually don't get that one. So I'm like, and they're like, mass. I'm like, yes. So the neutron has mass. So I said they had to wait this far to get the technology to start weighing atoms. Because, a lot of science has to do with technology development. If you don't have the right kind of microscope, you can't see the things that you need to see. So I said that they were weighing atoms, and the atoms were coming out heavier than they thought, which means that Chadwick then decided that there was something inside the atom that weighs something, but it has no charge. And that's called a neutron. And it goes like that. Okay, now the rest of this you can delete. I just threw in these, but they're not on the text or anything like that. I just thought that the kids might have heard of them before, and so this is, and then this was just funny. So, and then we go into this, and I draw this on the board, and I have the kids draw it into, like, they have the slide, but you can have them draw this into their notebooks, and because this is really important as far as hypothesis versus results, and then conclusions drawn from results. I mean, I just love this experiment. So I tell them that the box represents gold foil, and the circles represent alpha particles. And I say, okay, this is what he knew about alpha particles.
You said the box represents gold foil?
Gold
As
foil.
in which part? Just this right there?
The yellow box.
Oh, okay.
Yeah. So this is what I did. Let me try. So I said, okay, here's our alpha particles. And I said, okay, gold is an element. What did they know was inside an element? What had they discovered thus far? And somebody will say, oh, they've discovered protons and electrons. Okay, and how did they think they were arranged? Oh, they were scattered without. So I said, okay, draw this into your notebook. And draw this in your box. They think it looked like this. And I said, then these are alpha particles. And we know that alpha particles are helium nuclei. He didn't know that. But because they're helium nuclei, what kind of charge do they have? And we say positive. So these are positive. And then the other thing he knew was that they were bigger than protons or electrons. Okay, so then, just to make it personal, I picked the 3 biggest guys in class, and I give these names. Whatever, okay? And then I find the tiniest girl in class, and I make this the Trang. And so I said, okay, then they played...
The Trang? You said...
I have a girl named Trang. She's
okay.
like this big.
Oh, okay.
Okay, so... I said, then they played Red Rover. So imagine Joe and Nate and Sam playing Red Rover against a bunch of people Trang size. And everybody's like, snicker, snicker, snicker. And I'm like, what do you think is going to happen? And they're like, oh, they're going to get through. And I'm like, do you think they'll be able to get through straight, or do you think they'll like be deflected a little bit? They'll probably, go off course a little bit. So I said, okay, so they look like this. And then the kids draw this. Okay? And I said, this is what he thought he was going to get. And this is also on the slides. Where they're going to be deflected mostly. Okay, but here's what happened. And I say, the Joe particle, in fact, did go through and get deflected a little bit. The Nate particle actually went straight through. And then the Sam particle, I picked the very biggest guy, whoever it is, and the one who can take a joke, got rejected. And everyone's like, ah, ha, ha, you got rejected by Trang, whatever. And they're like, oh. So then I click on this, and I have them draw that, add that to their slide. And I say, so here we go. 4 out of my 7 particles made it straight through. Okay. you are the running back. And the running back, you are able to go straight down the field in a perfectly straight line. What does that tell you about what's in front of you? And you know how you're going to have enough football
Oh yeah, I love that
people
illustration. Yeah.
who know that means there's nothing in front of you.
Right.
Okay, so then the first conclusion is that since most of the particles are getting straight through, then atoms are mostly empty space. There must have been nothing in front of Nate there. And then I said, okay, now, we all know that Trang standing in front of Sam is not going to be able to stop him. So, but something did stop him. Now, there's nothing bigger than a proton or an electron, so how could we take Trang and work it out so that she will be able to stop Sam? And they realize that you have to put a bunch together.
Right.
And so then I say, okay, so you should redraw your box like this. And I say that they knew that the clusters were protons because they knew that the electrons were like the size of dust. And like a pile of dust is still a pile of dust. It's nothing. And so then the alpha particle is getting bounced off of that. And so that's what's happening to this guy here. And then a few were just getting deflected because they happen to wind up getting close, but not actually hitting it straight on. And so then I said, so his second conclusion was that, first, atoms are mostly empty space. Second, there's something really big inside. And he called that really big thing a nucleus. And so that's the big production with Rutherford.
That's ingenious.
I used to, back when we had more time,
Right.
I took all the kids outside, right next to the building. And I told them all to stand in a big mob next to the wall. And then I pulled out the three biggest guys to have them stand over here. And so then we acted this out. But we don't have time for it anymore. So I don't do it anymore. But I used to do that.
I love that idea. That's genius.
So, because, the bodily kinesthetic people,
Yeah.
they love to act it out. But at least by putting names on there, it helps them remember it anyway. It's more of the story approach than the act out approach. Because I've always had this dream of also acting out electron configurations and go outside and have the kids
run around
in circles and go in the dumbbell shapes and have different p electrons and stuff. But I never had time for that. I would love to do it. So.
Are we allowed to do that? Like, if we did have time for it, hypothetically? Like, we could take students outside and... Really?
Oh, absolutely.
Oh, wow.
There is one time that I do. I make the time in the gas law unit to take them outside, and it helps so much. I put a circle on the ground, and they are all molecules, and I blindfold them. You have to walk around inside the circle, and somebody has to count how many times they hit the circle, and that's the pressure. And then we put more kids in to see how that'll affect pressure, and then we make the circle smaller, see how that affects pressure, and so on and so forth.
That's awesome.
So that one I definitely I've held strong. I'm gonna do that. But this other one I sacrificed.
So how would we explain alpha particles to them? Are they supposed to know that already, or like?
The only reason why I say alpha particles are helium nuclei is because I've seen that show up on the TACS test.
Right.
Now, the way that the TACS test worded it, they didn't need to actually know that information, but a lot of times when the kids hit a test and they have not seen something before...
Yeah, it throws them off, kind of.
So I just mentioned that they're helium nuclei because of that reason. But all they really need to know is that they're positive and they're big. So.
The alpha particles are positive and big.
Because that's all Rutherford knew. That they were big and they were... And I talk about the fact that when he got this result, that he wrote a letter to his friend, and he told his friend that this result was as amazing as if you shot a cannon at a piece of tissue paper and it bounced off. And he literally wrote that. That was his analogy. So everybody's like, wow, when they hear that. So, and then we talk about, hypothesis versus results. How you have to change your hypothesis, and then,
And so, what do you mean by helium nuclei? Did he get was he shooting helium at the gold? Like
he was shooting helium nuclei at the gold.
Using the cathode ray. Or no, not the cathode.
This has nothing to do with cathode rays. It's they have a pretty good picture of the book. Unfortunately, I do not have the CD that goes with the book, so I can't pull the picture out and put it on my slide, or I would do that. But let's see, chapter 2. No, not chapter 2. Chapter 4. I don't remember. Here it is. So here's the picture of the cathode ray. 2, and here's his experiment there, Thomson's experiment, and here's the gold foil thing.
Okay, cool.
So that's where.
Sweet.
Yeah, and if you want to have your kids, pull out the book and look at the pictures, because it's more effective, then
Sweet.
fine. That's fine. Like I said, this slide is all review.
Mhm.
Hopefully they just know it.
Yeah.
You can skip it maybe.
Mhm.
Especially since, here you're talking about how neutron, on the previous slide, you talk about neutrons being neutral and stuff like that.
Mhm.
Now, for the next slide, the one you
Mhm.
were just on, you want to talk about protons, you want to talk about neutrons, but you can delete the part about electrons
Mhm.
and save that for later, and that'll
Mhm.
help you save some time. But you do need to talk about the isotopes, because that is
Mhm.
part of the text.
So electrons, it's on the text.
Well, it's not on the text for this.
Oh.
Electron, the charges is important here
Mhm.
when you start making compounds,
Mhm.
because of course it's all about the charges for
Mhm.
ionic compounds. So that's why I'm saying, since you're going to be talking about charges anyway,
Yeah.
later, instead of doing it twice, maybe you should just do it once. So that's an idea.
Cool.
And the next
And cations, anions, just kind of
cations and anions.
Anions.
Well, that's why I said you'll have to talk about those when you hit
when
that unit, but you don't
Mhm.
have to talk about them just yet.
Mhm.
And you don't have to do this. It's not on the text.
Mhm.
Now I will.
Was it on the text last year?
I don't know. I mean, I've always done it.
Yeah, because it's basic. It's like basic.
I know.
Essential.
This is but it's not there. So
Mhm.
I don't know if it's not there because they think it's so basic the kids should know it anyway, and they don't feel
Right.
like they have to specify.
You remember seeing anything like it on the text this last year? Or common assessments last year, or EOC?
Well, I never did get to see the EOC. They don't let us see it,
Oh, yeah.
so I have no idea what that looked like.
Do we even administer the EOC ourselves, or is it?
It's done on computers.
Oh, okay.
So they take them down to the computer lab.
Oh.
Nothing to do with it.
That's at the end of the school year, the EOC.
In May. I'm hoping they don't run the kids through the chemistry one. They did last year, so I'm hoping that means we're done. We don't have to do it again.
Mhm.
I don't.
How often do they do the EOC? Is it every?
Well, right now they're field testing it,
Mhm.
which means they take kids and they put them in the room
Mhm.
and they make them answer the questions, and the kids are so burnt out because they've already taken the tax, and the kids know it's not for a grade, so they don't care,
Mhm.
and so they score really, really badly,
Mhm.
which just makes our school look dumb.
How long has the EOC been around for?
Officially, it hasn't even started yet.
Oh.
So, but the field tests started
Started.
like last year, 2 years ago.
Oh.
I think 2 years ago.
And that's eventually going to take the place of the tax? But it's going to be pretty much the same thing, right? Just a different name for
Well,
it?
it's a standardized test, but it's not going to look anything like the tax.
Oh, yeah.
Because the tax is
It's more
IPC and biology, all
biology
mixed
and-
together.
yeah.
The EOC will be an
It's a separate
individual
test.
subject,
Mhm.
and theoretically a lot more rigorous
Yeah.
than the tax test ever was.
Mhm.
I don't think this was on the tax test. I don't recall ever seeing anything about it.
Mm-hmm. And EOC is being implemented like in the entire state of Texas, right?
Yes, next year's freshmen are the very first ones that are going to be taking it.
Cool.
So, there's good news and bad news,
Mhm.
like always. Yeah, so you don't have to do that. I do that. It's just kind of a fun thing, but you can
Mhm.
skip it. Save you 5 minutes right there.
Mm-hmm.
Talk about atomic number,
Mhm.
because you need to talk about how the periodic table is arranged, and
Mhm.
since it's arranged by atomic number, you have to do that.
Mhm.
You want to talk about the atomic mass, because we're going to talk about isotope mass and stuff like that, so
Mhm.
you need to do that. But you can skip the charge
Mm-hmm.
for now. Yeah, so you can skip this entire slide too. And then you do need to talk about this slide,
Mm-hmm.
because they have to know how isotopes are going to be written.
Mm-hmm.
Let me talk about this. Now, I draw pictures for this because the kids have the hardest time with isotopes.
Mhm.
So what I do is so click one more time and you'll see the example there for hydrogen. So, and you're going to want to hand out a periodic table to all the kids. I photocopy the tax periodic table because I want them to be the most familiar with that one so that when they hit the tax, that's not an issue.
Mm-hmm.
So I say, okay, here's the hydrogen,
Mm-hmm.
and we have hydrogen 1, hydrogen 2, hydrogen 3.
Mm-hmm.
All right, I said, look at your periodic table. How many protons does hydrogen 1 have?
Mhm.
And I should hopefully be able to say that it's got 1.
Mm-hmm.
And then I say, then it would also, since you're not talking about charge, just say, okay, that means it's going to have the same number of electrons.
Mm-hmm.
And then I say, okay, if the total mass for hydrogen is 1, how many neutrons does it have? They usually get this question wrong.
Mm-hmm.
And the answer, of course, is that it has none.
Mhm.
So then you reinforce protons weigh 1, so if the total mass is 1, it's it's only got one proton.
Mm.
And I said, okay, hydrogen 2, how many protons does it have? And hopefully they can come up with the fact that it's still 1 because it's hydrogen. And then I said, again, has 1 electron. And I said, okay, if the total mass for this is 2, how many neutrons does it have? And they usually, by this point, they're like, okay, now I understand. It's got 1 neutron. And then I said, okay, hydrogen 3, how many protons? And now they're all sort of in unison saying 1. And I say, okay, how many neutrons? 2. And I say, okay, these are different isotopes. And I like draw this in your notebook. So the point is, they're all hydrogen, but they all have different masses, and they have different numbers of neutrons. That makes them different isotopes. And I say then they react exactly the same way as each other.
Right.
And we talk about carbon. I say you're organic beings. Most of your body's made up of carbon, and there's 3 isotopes of carbon, but they all react the exact same way. They're just slightly different masses.
Right. Cool.
So, but that's where the pictures really help with those visual kids.
My computer's so slow.
Yeah, I know.
I'm waiting for these new computers.
Yeah, have fun with that. We'll see.
I know, hopefully. So does this change from year to year, just like the...
Not year to year, but they did make a change this year. So that's why I'm actually starting to look at it again. So skip this entirely.
Crap. I don't know what just happened.
It doesn't like you.
I know. Me and the computer have this love-hate relationship. That always constantly embarrasses me during the class, too. It's terrible, because you don't get all stalled. Does it ever do that?
Well,
You'll be like, all right, guys, next slide. And then you click it, and then they're just like...
and then...
And I'm just kind of like...
And now for a filler. Da, 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 da.
Yeah, I know, right? Da-da-da-da-da-da. Alright, let's see.
And we talk about how many teachers, now I say I don't do this, but a lot of teachers will on the first day tell you that your tests are 40% of your grades, stuff like this. So I said, well, let's pretend that we're in gym class, and the coach tells you that 80% of the grade is you dressing out, and 20% of the grade is your effort. And they're like, okay, I've heard things like this before, so it makes sense. Yeah, go ahead and click it. Keep looking. Yeah, because I say, okay, how do you take the average of something? They're like, add it up and divide by however many. I'm like, good. Now we're going to talk about a different kind of average. It's called a weighted average, because they need to understand that it's different. So then I say, okay, so you dressed out every single day, so you got a 100 for that grade at the end of the 6 weeks. And so you just click in the 100%. I said, but you decided you didn't want to do square dancing, and so you get a 70. And they're like, square dancing? Like, whatever. And so then I say, okay, what would you do to get your average? And they're like, okay, you add them up and divide by 2. And I said, well, that means it's 85. But that's predicated on the notion that 170 are equally important. And I said, are they not? Are they? And they said, no, the 100 means more. So then we estimate. I'm like, okay, does that mean your average should be higher or lower? And they should realize that it should be higher because the larger grade is more important. So then I show them how do you do it. You have to change a percent into a decimal, and then you multiply it by the value, and then you add them up at the end. And they're like, oh, 94, that's so much better. And then we go into the next slide. It's the steps on actually how to do that. If I were you, and I should have done this for my slides, on the next one, where it says multiply value, put mass in there. Multiply the mass by the percent abundance decimal. Because multiply value is a more generic term, but just go ahead and do mass. And I should have done that for mine. I realized it as I was teaching, but it was too late. So, and then add the results, and then we go through an example. And so I said, okay, what's the first step? And they're like, you have to change the abundance to a decimal. I'm like, okay, so what's this one going to be? And then the hardest one for them is, like, the 1.11 is not too bad. They know that they're supposed to move it over to, but a lot of times you see on the practice side, they have an abundance that's already a decimal, and they want to just leave it alone. I'm like, no, you have to keep moving it. So that's the thing you have to worry about. And then they do this, and then we round it. And I tell them to round it to whatever decimal places, like, don't round at this point, round it at the end, and round it to however many decimal places your method had, which on all of my practices is 3, because that's roughly what they have on the periodic table. So, and then this is where they pull out their whiteboards and they do it. And I only have them do 2. If you want to throw in another one there, that's fine. So, and then this is where we go back to Dalton, and so now they understand things about isotopes, and they understand things about, you know, the different things in the atom, and so that they can talk about, you know, that the fact that indivisible is wrong. You know, they are divisible, and I say, okay, what can they be broken into? And protons, neutrons, electrons. And then I say, okay, what about if they're identical? And a lot of them, most of them will say yes. And then you're like, and they're like, no. And I'm like, why not? And then somebody usually knows that it has to do with the isotopes. And if they don't, you just tell them. It's because of the isotopes. What does isotopes mean? Oh, neutrons. They have different numbers of neutrons. So I'm like, so they're not identical. And then we talk about, also on the average mass. When I first introduced isotopes, and I have that cobalt-58 example, I said, okay, find cobalt on your periodic table. What does it say? And it says 58.933. And I'm like, what would you round that to? 59. I'm like, well, why am I saying 58? And so we talk about, and I use their weights, and I say, if I wanted to, I could find the average weight of a person in this room. And I said, does that mean that that average is going to be your weight? And they're like, no. So I said, so there's a difference. On the periodic table, it's the average. It's everybody, all averaged together. But isotope means I'm talking about one particular person. I usually point at some kid. Like one particular person, and I'll give you that weight. So you're like, oh, okay. So, and then of course, by this point, by the time you get to number 3, they're used to saying false. So they think that's false. And I'm like, no, that was actually true. And I use the example of, so you can take carbon and hydrogen and oxygen and mix them together to make this. And I say, what is this? And usually somebody can figure out that's glucose. Glucose is an important molecule for them to know. So I say, see, and that's what number 3 is saying, that they can chemically or physically mix together, and these are whole numbers. You're never going to see a fraction down here. So that's number 3. And then number 4, I'm like, what do you think? And the problem is, you know, these things are wordy, and so they don't understand them, so they just guess.
How could I describe to them the difference between physically mixed together or chemically?
Well, you just finished Unit 3, so hopefully they know that. You know, chemically they're making bonds.
Yeah.
Physically they're just next to each other.
Next to each other, yeah.
And then I say 4, and they're like, yeah, I think that's true, and it is true. And I go back to my glucose that's on the board, and I say, see, it's carbon and hydrogen and oxygen mixed together, you still have carbon and hydrogen and oxygen. I'm like, if you took carbon, hydrogen, and oxygen, and when you did the reaction, you wound up with lithium, you know, that would be
chemically.
That would be meaning that one element's changing to another element.
Right.
And that doesn't happen. And then I talk about, you know, how do you get from one element to another? And it's like 50-50 whether or not you're going to have a kid in the class that comes up with nuclear reactions. So, and that's the last thing on there. I tell them to write that in there. You know, nuclear reactions will change it. And then we get into the periodic table, and they need to know all of this stuff. And for this, the analogy is a deck of cards. I say you can take a deck of cards and spread it out on the table and arrange it by suit, and arrange it, you know, ace to king, and you'll be able to see the repeating patterns. And then that's his scratch work, just so that they can get an idea. And I say, you know, here it is, and the beauty of this table is those question marks in there. It's like the same thing. Let's say you had a deck of cards and you're missing some cards. You want to figure out what you're missing, so you spread them all on the table and you organize them and you see where the holes are. And you can even predict exactly what card goes there. It's going to be the 8 of clubs or you know, Queen of spades or something like that. And they're like, yeah, I get that. I can visualize that. So we talk about that. And I point out the lithium, sodium, potassium, rubidium row to them. I'm like, these are all reacting the same way. And then we go to the next slide, and we do the modern periodic table. I point out lithium, sodium, potassium, rubidium. They're still in the same, but it's columns now. I say turn 90 degrees. So that part doesn't take very long at all, talking about the periodic table. And then this is where I played the game. And you'll just have to see, you know, how you're doing. Like, before you start the unit, set the date for the test. You know, decide that this is going to be, theoretically, it should take you 3 days to talk about this, and then you should have a test on the 4th day. You may be able to get away with 2.5 days. You know, we'll see. Especially if you cut this out, because I got mine done in 3 days. So if you do shorter, you can maybe do 2.5 days.
Yeah, that's what I'm trying to shoot for, just to get caught up.
So.
It's gonna be on the tax.
Yeah.
So
it will be on the tax. And I'm like, I don't know how they're going to phrase it this year, but I guarantee you it's on there. And usually you'll have like a senior in your class who's already taken the tax, and they're nodding their head. They're like, yes, it was on there. You know? So, and then they need to know those names. I also usually hit up the transition medals. It's not a particular family, but it is a group. But most of them have heard of that before too.
You make sure that they look on their periodic tables too, just to see like the.
Yeah, well, I'll put up like 1A, alkali metals. Okay, somebody give me an example of an alkali metal. So they have to look on the periodic table, and they're like, oh, lithium, something like that. So I have them give me examples of each ones to make sure that they know where they are.
Okay, cool.
I call the periodic tables their best friends because I don't like saying the phrase periodic table. It's kind of annoying. So I'm like, get out your best friend. You're really your best friend. I'm like, just like your best friend, you don't want to ever leave this at home. You want to bring it to school every day. And you can use your best friend on your test. And I'll tell you secrets. All kinds of secrets.
So what do you mean by this? Left of stair?
So on the periodic table.
Oh yeah, you're talking about the
stair
okay.
step, and the metals are on the left of it. Now you can delete the form cations and form anions part because you're not going to talk about ions.
Okay.
Or you can leave it and say, and we're going to talk about cations and anions later. It's up to you. And so then they just have to do this little scavenger hunt, and find the families. And I always tell them, because on the tax periodic table they have Arabic numerals and Roman numerals, and I say we don't want to look at the Arabic numerals. They're not very informative. So I don't know why they put them there. And then, yeah, this is basically my rewording of a question that I've seen many times on the tax. Tax is multiple choice. So I put up an element, and then I say, okay, which element is it? And then you put up the 4 choices, and you say, okay, which one is going to react like this one? And I've seen like that same question. But they use different words, like react like, have the same chemical properties as, different. They phrase it differently, but that's the same question. And then they're supposed to figure out this oxygen, and they say, why? And they're like, because it's in the same column. And I make them do the hand symbols. I'm like, this is a period. This is a column. I'm like, everybody, hold up your hands. This is a period. This is a family. So it's, again, the kinesthetic. And so that one is where I talk about iron, the fact that iron is in, I call it the redneck period because they're in a triple wide. And the kid's like, oh, miss, that's not nice. Okay. And so cobalt being next to iron is still in the same family. And that's just one special feature of the periodic table. And this is the very last slide, and if I have a few minutes before the bell's going to ring, I talk about science fiction writers and how they have silicon-based aliens instead of carbon-based aliens. Sometimes you'll hit a couple kids that way.
Sweet.
So that's
awesome.
Unit 4 in less than 20 minutes.
Nice.
Speed teaching.
I know, right? Thanks. Yeah.
Well, it means it's reacting with you.
Right.
So,
yeah.
Irritating, it turns red, it starts to burn, it starts to itch. It's the chemical is reacting with you, which is a chemical property.
Right. I try to use like have you seen Fight Club?
Yeah.
Yeah, I try to use that scene whenever Edward Norton and Brad Pitt, he drops the acid on him, and it's just like reacting with your skin. Like it's like, guys, look on a molecular level. Whenever acid touches your skin, what's happening on a molecular level? It's not just burning. We're not talking about the physical aspect of you feeling pain. I mean, even though that's what's happening, we're talking about just on a molecular level. It's burning. It's actually reacting with your skin and burning.
It's killing you.
Yeah.
And the thing about the chemical and physical properties and chemical and physical changes. They hit it so hard on the tax test, but honestly, if you talk to a real chemist, they don't really know. Like, there is no set definition for
physical, because it seems like it's kind of just like and that's what they were getting kind of confused on.
Exactly. So we have